scale voltage that the voltmeter can measure divided by the total counts. The total counts in this case can be written as from 0 to 9,999, this voltmeter will have 10,000 counts. So therefore, the total count is going to be equal to 10,000. Therefore, resolution is going to be equal to 9 divided by 10,000, which is going to be, in this case, the value is going to be 0.9 millivolt.
In this problem, we have to evaluate the value of integral 0 to infinite e power minus x square plus y square dx dy. Now, this can be written as 0 to infinite e power minus x square into e power minus y square dx dy. It is nothing but 0 to infinite e power minus x square dx into 0 to infinite e power minus y square dy. Limits are constants, so 0 to infinite e power minus x square dx, 0 to infinite e power minus y square dx, you can write. Now this value is root pi by 2. This value is root pi by 2. Therefore final value is pi by 4. That is nothing but 0.785. How this value is pi by 2? I am explaining here. Let us take x square is t, x is root t, dx is 1 by 2 root t dt. When x is 0, t is 0. When x is infinite, t is infinite. Integral 0 to infinite e power minus x square dx can be written as 0 to infinite e power minus t 1 by 2 root t dt. 1 by 2 into 0 to infinite e power minus t power minus 1 by 2 dt. 1 by 2 0 to infinite e power minus t power 1 by 2 minus 1 dt. 1 by 2 gamma 1 by 2. It is nothing but root pi by 2. That's why I have written this is root pi by 2, this is also root pi by 2. Root pi into root pi, pi by 4, that is 0.7. We have to evaluate the integral 1 by z dz. Along the semicircle mod z equal to 1. Along the semicircle mod z equal to 1. So radius 1, angle theta. Now, if I is equal to a plus bi, then the value of b is. So we have to evaluate this integral. So z equal to r into e power I theta. So integral 1 by z means 1 by r into e power I theta. Differentiation of r into e power I theta is r into I into e power I theta d theta. Now radius is 1, that's why integral e power I theta cancel, I d theta in the interval 0 to pi. Now, so I into pi, I pi. Now, given that a plus ib equal to I pi, then what is the value of b? The value of b is
in this question we have to calculate Norton's equivalent across the terminal x and y. Okay. So first of all, let us suppose a current SC short circuit is going through this, and then let us suppose a current, this is I1, and here the current which is flowing is I2. Now we have, suppose this point voltage is V1, so we have I1 is equal to V1 by 6 and I2 is also equal to, this is short circuited, so it is V1 by 2. Now If we apply KCL at this point, then I2 entering and plus 6 I1 entering is equal to ISC, equation number 1, short circuit current. Also, if we apply KCL at this point, then we have I1 outgoing plus I2 outgoing plus B1 minus 9 by 3. B1 minus 9 by 3 is equal to 0. We can calculate the value of put I1 and I2. I1 is B1 by 6 plus I2 is B1 by 2 plus B1 by 3 is equal to 3. Solving, we have B1 and that B1 value is equal to 3 volt. Now if we have calculated B1, then ISC can be calculated as I2, that is B1 by 2, so 3 by 2 plus I1, 6 I1, that is 6 into I1, B1 by 6, that is 3 by 6. So it comes out to be that is 1.5 and this is 3. So this is 4.5 ampere and this value is equal to Norton's current. Now we have to calculate RTH, Norton's resistance. So first of all, let us calculate open circuit voltage, VOC. Now if it is open circuited, then the same current 6 I1 will go through this. So in this terminal 6 I1. Now if apply KVL, let us write this value I1 here. IN is 4.5 ampere. VOC can be written as minus VOC plus 6 I1 into 2 plus 6 I1 plus B1 directly. This is B1 is equal to 0. So VOC is equal to 12 I1 plus V1, equation 2. Now we have to calculate I1 V1. I1 can be written as V1 by 6. I1 can be written as V1 by 6. And also we can apply KCL at this point. Then KCL will give us B1 by 6 plus B1, this B1 minus 9 by 3, this and this, plus B1, this is the current 6 I1 plus 6 I1, it is entering, so it will be minus 6 I1, minus 6 I1 is equal to 0. Putting the value of I1, V1 upon 6 plus V1 upon 3 minus 3 minus 6 into V1 upon 6 is equal to 0. So it will be equal to B1 plus 2V1 by 6 minus 6B1 by 6 is equal to 3. So it comes out to be equal to 3 minus 3, that is 3 minus 6, that is minus 3V1 is equal to 18. So V1 is equal to minus 6 volt, and if V1 is equal to minus 6, then VOC can be written as 12 into I1, that is minus 6 by 6, that is minus 1, plus B1 is minus 6, so it is minus 18 volt. VOC is minus 18 volt. Now R Norton can be calculated at VOC minus 18 volt upon RS, that IN 4.5. So this comes out to be equal to minus 4 ohm. So Norton's current will be 4.5 ampere and Norton's resistance is minus 4 ohm, which is given in option B. So answer for this question is
block diagram representation of a system is given whose open loop transfer function is K upon S plus P. Question is, if the percentage overshoot for the step input is 9.478% and if the steady state of a ramp input is 0.01, find the values of K and P. From this we can obtain the closed loop transfer function to be K upon S square plus PS plus K. Since S square coefficient is 1, omega n of the system is root K. 2 zeta omega n of the system is P. Zeta is P by 2 root K. It is mentioned that percentage MP is 9.478%. That means e to the power minus zeta pi by root 1 minus zeta square is 0.09478. From this we can obtain the zeta of the system to be 0.6. This is 0.6. It is further mentioned that steady state error of the system for unit ramp input is 0.01. This system is type 1. So steady state error of a type 1 system for ramp input is given by 1 by kV, which for this system is P by K, and this is 0.01. We have the relation between the P and K. P by K is given to be 0.01, P by 2 root K is 0.6. There are two equations and two unknowns. From this the value of K becomes 14,400 and the value of P becomes 144. Answer to this question is A. Open loop transfer function of a system is Ks plus 4 upon S plus 2 S minus 6. For K greater than 4, what will be the stabilities of open loop and closed loop systems? This open loop system is unstable because there is an open loop pole in the right side of S plane. Whereas, finding the characteristic equation, it will become S square plus S K minus 4 plus 4K minus 12 is equal to 0. 1 plus G of S H of S. Closed loop system stability depends on the roots of the characteristic equation. Since it is a second order system, necessary condition itself is a sufficient condition for stability. That is, all the coefficients of the characteristic equation should be present and must have same sign. So condition K greater than 4 and K greater than 12 by 4, 3. So hence we choose K greater than 4 as the final answer. Since it is mentioned that for K greater than 4, the closed loop system is stable, answer to the question is B.